Previously, we talked about equilibrium conditions in a plane. That's two-dimensional problem. But this time, we need to talk about equilibrium conditions of a particle. We'll still talk about one single particle. That's mean 1 point. But this time is in three-dimensional setting, in space. Okay? So that's also very simple because based on Newton's law, Newton's first law is okay in two-dimensional, but obviously is also okay in three-dimensional. Two-dimensional, that means you have two equations. But this time we're talking about three-dimensional. Then, of course, you have three equations because all the components in x, y, and z directions are 0. So that we just basically collect all the x components, we add them together based on the free body diagram, and this is what you got. And you basically collect all the y components, put them together, and set equals 0. In addition to these two, we have a third direction to make a three-dimensional problems. Then you collect all the z components and add them together equals 0. So the theory is very simple. We just need to apply to solve three-dimensional problem. So this time we have three equations, allowing us to solve for three unknowns this time. Okay? So I just want to talk about one more example just to show you how we can deal with these kind of particles with the forces in equilibrium. But first of all, we need to plot the free body diagram. Okay? So let's look at this example. So obviously this three-dimensional setting. There is a 200 kilogram cylinder, this one. So the self-weight is a 200 kilogram cylinder. Is hung by means of two cables. So these are two cables, cable AB and cable AC, which is also attached. These are attached with this vertical wall. Okay. In addition, there is a horizontal force P, this horizontal force P, which is perpendicular to the wall, to hold the cylinder in the position shown. So which means to hold that, that means it's in equilibrium, right? Okay. Now, we need to calculate or determine, number one, the magnitude of this force P applied, the horizontal force. Number one. Number two, and number three, we need to calculate the cable forces, the magnitude of the cable forces, what we call the tensile forces, tensions in each cable. That's cable AB and cable AC. So if you go back to look at this one, number one, you need to figure out that is whole thing is under equilibrium condition. If you look at this carefully, right, you apply the horizontal force to hold the cylinder in the position shown. That means that has to be the fixed position. That means in equilibrium. And there's a three-dimensional problem. So obviously we are finally should have these kind of three equations. And then we just do a simple check. How many unknowns? Three unknowns. Wow, that's good. So all we need to do is to get these three equations. And combine those three equations. We can solve for these three unknowns. Okay? So what I'm going to do, this time I tried this DocCam again to show you step by step for solving this problem. So hopefully this time it's going to work. Because actually I tried. The light was off. That's why last time it didn't work. I called them, but they may not come. Let's say later, they're going to come in later. So I'm going to write in the maybe a bigger font, right? But I don't understand why it is kind of blue here. What's this? Oh, maybe there's a... Okay, I think I'm going to write with this kind of a pink-orange color to see if it doesn't work. I'm going to change to a different color. Okay? Okay, if I have a question in the process, let me know. Because sometimes when I write something, if you do not understand, just feel free to interrupt me. Okay? So again, we are talking about this example. Number one, we have this point, which is called the point A. That's the particle we can focus on. So first of all, the step number one, we need to plot what we call the free body diagram. Is that clear? Okay, so let me use the green color pen to see maybe this is maybe a little bit better. Okay, so free body diagram. Okay, So obviously we pick point A. So this is the point A. So this is the point we want to plot the forces on, okay? So first of all, we have the cylinder, right? So the cylinder has a 200 kilogram self-weight, which means there is a force going down. So don't plot the cylinder. Instead, you plot a force to represent that cylinder because it's due to his self-weight, right? So what is the magnitude of self-weight? 200 kilogram. Let me tell you, the self-weight normally is given in terms of kilogram, but kilogram itself is not the unit for force. So again, I was telling you in the first chapter when I went through those basic concepts, right? I said in international unit, if ever you see the kilogram, you need to transfer that kilogram to Newton. So always remember, when you see a self-weight in terms of kilogram, you need to have 200 kilogram times 9.81 to transfer to Newton. Okay, so you punch your calculator, whatever result you got, that's in terms of Newton, and that's the force unit. So make sure for any international unit you are dealing with, if you see a kilogram, make sure you multiply with 9.81. Okay, so that's the first force acting on point A. Second force, there is a horizontal force called P acting on point A, and that's fine. So we just need to plot. There's a force P here, and we don't know the magnitude because we need to calculate the magnitude. Well, that's why we use a symbol called the P. So finally, we need to calculate P equal to what? Okay, number 3, at the point A, there is a cable force going to that direction from A to C. And we don't know the magnitude either. If we don't know the magnitude, then what? Then we can call TAC in that direction. Okay, so that's a symbol I use. One more, there's a cable AB. And we do not know the magnitude of cable AB either. So then we call the TAB. And with this direction. Okay? And no other forces at point A. And then that's what we call the free body diagram. So we add all these, how many? 4 forces together equal to 0. That's an equilibrium condition, in fact, right? But before doing that, we need to calculate or identify or say calculate the 3 components of each force separately. And then we can add them together. Okay? So that's the first step. Plot the free body diagram and we're done. Number 2. I think the blue one is due to, I think it's this. Okay, that's good. That's better. Okay, now I figure out. Okay, so number 2, calculate each force components, right? So let's start from what? Let's start from this self-weight. Okay, self-weight cylinder. So cylinder force, let's say cylinder force, I don't give a name, let's give a name, G. Okay, so that's the self-weight of that cylinder. So G is a vector because that's a force, right? So that vector is equal to what? Well, we just talked about any 3-dimensional problem. When you deal with a force, you transfer 100% physics into a 50% physics and a 50% math, which is called G times lambda. So this G is different from this G because I don't have the arrow on top. So this G is simple, which is 200 times 9.81. That's G, because that's magnitude, and times lambda. What is lambda? Well, before we talk about the directions, in fact, we need to set up the coordinate system for this problem. The problem itself doesn't give us. So then it's up to us to set up the coordinate system. Okay? So 3-dimensional coordinate system, so we can do anything we like. However, I want to follow the solution we have from the book so that I will have the same answer with the book finally. So the coordinate system setup is here. At this point, this is the bottom layer of the wall, and I call this one is X. And I call this one is Y. And I call this one is Z. Okay? So if you do not like this one, you can pick up another original point. For example, pick it here, you'll pick it here, you can pick here. It doesn't matter. your solution should be the same if you do it accurately, if you do it correctly. Okay, but this is what I choose because the book chooses this. Okay, so at this point, which is the original point, like call point O. Now, at point A, the self-weight is going down always, which is a vertical, right? So that is always in the opposite direction of Y if you look at my coordinate system setup. So that, what does that mean? So this direction is going down, so then you only have the Y components, which means J, and which is a negative. If you really want to write X component, that's 0 times I. If you really want to write the Z component, that's 0 times K. But they are 0, that's why you don't need to worry about it. Okay, so for this force, you may say, well, do I need to use G times lambda and then I use picking up 2 points to get the lambda? If you want to do it, that's fine. It takes additional 5 to 10 minutes. But you obviously know this self-weight is always going to the opposite direction of Y, which is negative J. Then you figure out in just 1 or 2 seconds why you want to pick 2 points if the problem is simple enough, right? So that's why I just write down the 3 components of the self-weight directly. In other words, this is the Y component, X component 0, and Z component Fz equals 0 for this first force given by the cylinder. Any questions? Okay, so then let's move to step number 3. Step number 3 is to calculate another force, 3 components. We pick whatever we like. Let's pick this one, P. So now let's talk about force P. We do one by one. We have to deal with the cable force later, right? Let's do it one by one from simple to complicated cases. So what is P? This P is another force acting on point A. Again, the left-hand side is physics, right? 100% physics. Now we need to write on the right-hand side. So 50% math, physics times 50% math, which is a P times lambda. So again, this P is different from this P because the left-hand side of the P is a vector. That's why I put the arrow on top. The right-hand side of P is a magnitude of the force. So although I do not know this magnitude, I just use this symbol called P, but without arrow because this is a scalar. In other words, this is one unknown. If you look at the left-hand side, there can be 3 unknowns. The right-hand side is the amplitude, the magnitude. That's only one unknown. Okay, so I use a symbol called P. If you don't like P, you call it something else, F, whatever. That's fine. So that's a P times lambda. Lambda is a unit vector. It's a unit vector acting on point A in this direction. And the problem statement says it is horizontal. Right? They said that somewhere. Horizontal. Here. It's a horizontal. If it's horizontal and we set up XYZ coordinate system, that means it's in X direction. Correct? It's not only in the X direction, it's in the positive X direction. So if it's in positive X direction, what is lambda? The lambda equal to I. In other words, there's no J direction, no Y direction, no Z component. So in other words, this is very simple. It's just P times I. If you really want to write the other 2 components, that's fine. You use 0 times J plus 0 times K. But obviously you don't need to because these are zeros. Okay, so the reason I can quickly write down those 2 forces is simply because they are simple. Okay, now we want to move to general. And then I will show you the general following exact the formulation I just gave you. Okay, number 3. Number 4, step number 4. Calculate a cable force because we have 2 more forces to go, right? Let's start from this TAC. What is the TAC? TAC is a force acting on point A, going to this direction to C, right? That's a cable force. So 100% physics, which can be split into 50% physics, that's called TAC, multiply lambda with the math. Okay? So this TAC is different from this because this is the magnitude. It's a scalar. And we do not know. That's fine. We use a symbol. Okay? That symbol is just called TAC. Or you can use some other names. Okay? Times lambda. What is lambda? So this time lambda is a kind of arbitrary, right? Because it's not horizontal, it's not vertical, it's not in Z direction either. It is going this, right? So then obviously we need to go back to look at that unified formula to calculate the unit vector. So if you recall what we just did 10 minutes ago, how to calculate lambda, all we need to do is to find 2 points, okay, in that direction. So this is the fourth direction, or this is the fourth direction. Do we have 2 points?
Yes.
At least we have 2 points, right? So we have a point A, and we have point C. And not only that, point A is a start point. Point C is an end point. This you need to identify. If you say, no, I think this point C is a start point, then that's wrong. You have to figure out, because it's cable again. It's a cable, right? So when we talk about cable force acting on point A, that is going that direction. So again, point A is a start point, and point C is an end point. So once we realize this, then what I need to do is to write this lambda, which is C subtract A divided by CA, or AC. And that is lambda. Okay, so use the end point, subtract the start point, and then don't forget to divide it by the distance between that 2 points. Okay, so specifically, I need to move up, right? So TAC is still here, times point C. We need to identify 3 points, 3 components of that point C. That shouldn't be difficult to deal with. Go back to look at the original picture here. Point C. Let's figure out the 3 components, right? So the Cartesian coordinate system is here, and this point C is on this wall. So then x component of point C is 0. Y components of this point C, 12. Z components of this point C, negative 10. It's going to the opposite direction, okay? So let me write down here now. We just figure out x component is 0, y component is 12, z component is 10. Okay? Any questions? Thank you, right. I did say it, but I forgot to write it down. Yes?
Isn't your x component 1.2?
Okay, we are going to use that later. But 1.2 has nothing to do, we are going to use that number. I'm not saying we're not going to use, but this 1.2 is a distance from point A to this plane, to this wall. But we are right now talking about point C. We haven't talked about point A yet. So in point A, we're going to use 1.2, okay? Any other questions? Okay, so now we got the 3 component point C. We need to subtract the start point. Now we need to use 1.2 at somewhere. Okay, so what are the 3 component point A? Point A is here. What is the x component point A?
Negative 1.2.
It's a positive. Who said negative? It's positive to the right, okay? It's to the right. It's a positive, okay? So positive 1.2. What is the y component of point A? 2, right? Okay. What is the z components of point A? 0. Good. Okay? So this is called the x2, y2, z2, x1, y1, z1. And then don't forget, divided by the norm or the distance. Then you just basically say square root 0 minus 1.2 minus 1.2 square plus 12 minus 2. What is the 12 minus 2? That's 10 square plus minus 10 minus 0 square. And then don't forget square root. Okay, and the Pound-Shell calculator, you can simplify this one. I'm going to write the solution for you right now. That is I think this denominator is in fact equal to 14.9193, and then you finally end up with negative 0. Because 0 minus 1.2 is negative, so that means negative 0.08455 divided by this one, and then times TAC. That is the x component. And then y component, 12 minus 2, that's 10 divided by this one. That's going to be 0.7046 TAC. That is the y components times j. And then z component minus 10 minus 0, that's still minus 10. So that's going to be minus 0.7046 TAC, or I say plus, but it's minus sign inside, and the K. Okay? Any questions? This is a standard now, right? Because the cable direction is kind of normal. That's what we got. So in other words, we got these three components of cable force TAC. So now let's move to the next one. All right, so this is step number 4, right? So step number 5 is to calculate this T force, TAB. So we calculate this one. So basically, this is another 100% physics split into 50% physics. There's a magnitude multiplied with lambda with the math. So what's the TAB? We don't know TAB, but we just use a symbol. It's called TAB with the magnitude multiplied with lambda. This time, what is lambda? That's the same thing. So going back to look at this original picture here, this time we have cable AB here, right? So cable AB, which is a force from A to B. So then, in order to calculate lambda, what is lambda? All we need to do is to find 2 points this time along this direction, AB direction. Obviously, we can find 2 points. That's point A, point B. And you need to figure out point A is the start point, point B is the end point. Right? So then it's going to be B minus A divided by AB. Times B minus A divided by AB. Okay, so then what we need to do is to figure out these components, and then we do the math. So point B, what are the 3 components of point B? Point B is here. What is the X component? 0, right? Point B. What is the Y component? 12. What is the Z component? This one, 8. That's positive this time. Minus point A. The 3 component point A has been figured out already, printed from here. So let me just write it down. Minus 1.220. Okay? And then divided by the norm, the distance. The distance is 0 subtract 1.2, that's negative 1.2 squared, plus 12 minus 2, that's 10 squared, 8 minus 0, that's 8 squared. Okay, so let me give you the final answer for this one, TAB. TAB finally, negative 0.09330 times TAB I plus 0.7775 TAB J, and then plus 0.6220 TAB K. Okay? Any questions? Okay, so now we have collected all 3 components for the forces. Then what we are going to do next is to apply Newton's first law. Those are the 3 equations, right? So what are those 3 equations? Summation of all x components of forces equal to 0. And the summation of all y components equal to 0. And next one I'm going to write later. So let's do one by one. So let's collect all the x components. So let me try to move up a little bit so that you can still see those components. Okay. Okay, now I can write down this one. Summation Fz equal to 0. Okay? Okay, so for the first force, it's called the G force, cylinder force. Cylinder force. We don't have x component, we don't have y component, we don't have z component, we only have y component. Then just put this number here, negative 209.81. Okay, so that's the contribution of force G into these equations. Because they only have y component. That's why you put the non-zero y component there. So then we're done with the first one. Now second one, P force. Force P. Force P, we only have x component. So then you just put P here. Okay? So then we're done with this one. So now let's move to the next one, TAC. Finally, TAC is here. Okay, so this is the TAC. So we have three components. Then this time we have to write three components separately. This is the x components. That's a plus negative 0.08455 TAC. Okay, so this is x components. This is the y components. That means plus 0.7046 TAC. This one. And then the z component is negative 0.7046 TAC. Okay, so x, y, z components from cable AC. Any questions? Okay, then we need to collect the last force, which is TAB. Okay, so TAB. What are the three components TAB? They are here. So this is the x components. So then plus negative 0.0933 TAB. This one. And this is the y components plus 0.7775 TAB. And then this is z components plus 0.6220 TAB. Okay? So we're now ignoring any other forces. There's no other force. There are only four forces, right? So then you say this equals 0, this equals 0, and this equals 0. So combining these three equations. So now we just need to do a math, right? So these are the three equations. 1, 2, 3. And how many unknowns? Number 1, number 2, number 3. Then that's perfect, right? So do your math, you get these three magnitude. Okay, so let me just give you this one. I'll let you go. So finally, after you combine those three, you finally end up with P equal to 235. So finally, don't forget this. It's called Newton. Okay, so your final answer must be with a unit. And then TAB 1402. That's Newton. TAC 1238 Newton. Okay, so then we solve the problem because finally these are the three things we are asked. Okay,